Oh, hey Gabby, what's going on?
Well, I'm trying to build a green screen. I wanted to use Haskell, but that didn't work. So I'm using Python and I keep getting runtime errors. I wish there was a way to catch these earlier.
Yeah, well, let's have a look, see what's wrong.
Okay, so I don't know why, but when I run my network, you can see this error.
I think you need to switch lines 42 and 43 around.
Okay, well, that did work, it's running, but now I'm getting the wrong shape.
Are you doing digit classification? Feels like that should have 10 outputs instead of the one you've written.
Good spot! If only I had some way to guarantee the correctness of the structure of these networks.
Wow, sounds like you might want to try using Grenade. It's a neural network library in Haskell. It enforces strict typing of the network so that you can statically check shapes at compile time.
The neural network library in Haskell. How does that work?
Well, we've spent the last 3 months improving the Haskell ecosystem, exactly to facilitate development of green screening software with neural networks. Let me show you what that network would look like in Grenade so you can see what's wrong.
That looks good. Tell me more.
So in Grenade, a network is represented at the type level by two type level lists. The first one is the layers. We can represent any series parallel graph like this. The second list represents the shapes. We use this to ensure the network is well formed. You can see the network you wrote is giving a type error. Let's give Theo a call.
Hey Bruno, I'm guessing you want me to explain our work on Grenade again. So when we started work on Grenade, it was incredibly immature. It did not have a nice user interface, which led to a very steep learning curve and difficulty using it. It lacked too many features for us to be able to use it to implement the models that we wanted to. This led us to decide on our two key goals. The first was to improve the user experience and make Grenade a library that someone could pick up quickly for a machine learning project. The second goal was to add support for a few industry standard neural networks. Specifically, we wanted to add support for an image classification network, an object detection network, and a super resolution network. This was to prove that Haskell could be used for some serious neural networks. So first I want to show you how we improved the user interface. So this is what it used to look like to train a simple convolutional neural network on the MNIST dataset, which is just a collection of images of handwritten digits. As you can see, there's quite a lot of code, and it turns out that most of this code is actually just boilerplate. So this meant that if someone wanted to train a neural network, they needed to handwrite the code for performing epochs of training. And this takes the experience away from creating the perfect model for a task and forces the user to concern themselves with the logic of training. Now, we have an extremely easy to use interface to train networks with supervised learning. This is what it looks like to code the MNIST network that we were talking about before. If we run it, you can see it gives a log of the current progress, giving assurance to the user. Here's an overview of the other things that we implemented in Grenade over the project. So we've added a collection of important loss functions and their derivatives, so users can easily use Grenade in any situation without having to worry about implementation details. Related to this, we also added support for mini batch training, which is extremely common in any neural network framework. It was also essential for us to be able to implement batch normalization, which is a required layer in the models that we were aiming to implement. Furthermore, we added a large number of layers, which you can see on the slide. And we had to rewrite a lot of the old layers to support new features. For example, convolutions now support padding and biases, allowing more freedom in defining neural networks. Leaky Rally was fixed to avoid some bugs that we caught as we expanded testing, and now supports a variable parameter. We also support 4D tensors now, which allows for greater, more complex networks to be defined in Grenade. When we demoed the framework to our supervisor, a very fair criticism was that the performance was extremely poor. Running a forward pass on a network with 20 convolution and pooling layers took around 7 seconds. Here's a plot showing the performance increases over time. There are a few things we did to improve these to achieve these speedups. For example, we used more performant algorithms for convolutions, which is a large proportion of many neural networks. We also migrated performance critical code to C to optimize array operations much better, and we can now run a network of this size in around 80 milliseconds on a mid-tier i5 processor. So, Gabby, what did you think about that?
That's really cool, but I've already done all of this work. I don't want to delete all of my pre-trained models.
Ah, I've got good news for you. What if I told you there was a way for us to load Onyx models in Grenade? Let's get Jason on the phone. He knows more about this.
We got a module that does exactly that. Initially, although networks in Grenade could be safe downloaded, it was not done through a standard serialization format, so it was not possible to use pre-trained models that were built using other libraries. The solution then was to add support for Onyx, an open source format for machine learning models. Most libraries like PyTorch and TensorFlow already support Onyx, so as a result, there's a lot of models available in the format, making Onyx an effective choice for users hoping to use only pre-trained models, without wasting time and effort training them and figuring out how they work. Underneath, an Onyx model is represented as a directed acyclic graph, where nodes correspond to network layers and edges represent inputs and outputs of layers. As we can see, each node also contains several attributes that describe the layer it represents. For example, the operator type defines the operation carried out by the layer, and since this is a convolution node, W will be the weight of the layer. Since networks in Grenade are represented as series parallel graphs, when loading an Onyx model, we first parse the directed acyclic graph into our internal series parallel graph representation. The loading of the network itself is done through the Onyx loadable type class. To load a network from the graph, each layer of the network must implement Onyx loadable and load their own attributes. The Onyx loadable instance for a network will compose the loaded layers into a network. Although it may sound complicated, loading Onyx models is actually very easy. With the function load Onyx model, all you need to do is give it the path to the saved model and the type of the network. If for some reason the model cannot be loaded, for example, if you're trying to load a convolution layer from a ReLU node, we stop loading immediately and generate a helpful error message explaining why and where loading failed.
Even if all of that's true, there is no reliable way for me to stream video into the neural network, and I need that for my green screen project.
You'll never guess what a certain group of students also implemented. Yep, it's a video streaming library, and I Skyrocket on the phone.
In order to be able to develop neural networks dealing with an input from a webcam, there was a need for a video streaming library. This library had to, at least, deal with the low-level v4l2 API, which enables webcam data access, and convert it into a form suitable for a Haskell program. Due to limited options available, a library had been developed from scratch. It was opted that this piece of code is uncoupled from Grenade, as it has the potential to benefit completely different kinds of applications. Developing such a library in Haskell has its perks. Haskell allows for type constant declaration. At a first glance, they do not seem useful. They're not being used to represent any variable or constant. Rather, they're used to represent a state, here representing either unopened, opened, or streaming state. This is utilized by the API. By defining it in this manner, it is impossible for a user to try to call a function with the device in the wrong state. This completely prevents, for example, an attempt to read from an unopened device. The start capture function takes in the device O, while an unopened device will have device U as its type. The GHC compiler will detect a type mismatch. Our library is not a minimal viable product, but rather it implements additional useful functionality. These include video cropping, video file generation, and video display.
Wow, this all sounds so useful. How do I start using it?
There is a handy website where you can download the library.
That's all well and good, but how would I even get started? If only there was some sort of tutorial.
Good thing we've covered that as well. Let's see what Apoorva can tell us.
Yeah, so thinking about our end users, we actually made an application to showcase the capabilities of Grenade and to let our users get to grips with the library. To do this, we used YesOdd.
Oh, I love YesOdd. It's nice how its DSLs help abstract the boilerplate code away. Its principles also align very well with Haskell as a whole. It uses types to catch as many errors as possible at compile time. Wait, did you write a web app then?
Not exactly. We use Electron so that it can run natively on your machine. we used YesOD as using web technologies allows us to have greater control over the interface. Let's look at the application now. And let's go to the tutorial. So the tutorial gives us an editor and some space for console output. This really allows the user to get stuck right in without having to set up an environment first. This neural network is attempting to learn the shape of a circle. What if we change some parameters like the examples? So if we set the number of examples to 100, we'd expect the network to perform much worse. And indeed, if we look here, it doesn't really know what a circle looks like anymore. Aside from this, we also implement some classic networks like MNIST for hand-drawn digits. While this is trained entirely in Grenade, we also have examples of networks loaded using the Onyx file loading module. For example, super resolution, which takes an image and scales it up by 3. Now let's have a look at image classification. Moving on to some industry standard networks now supported in Grenade. ResNet 18 is an image classification network. On my machine, which has a 6th gen i5-6500 processor, this runs in 50 milliseconds. Let me turn on the video feed so you can see me again. What's happening here is we're using our video streaming API over a local WebSocket connection to stream the data from the webcam onto a canvas in the front end. ResNet 18 is trained on the ImageNet dataset, so it can detect 1,000 objects. For example, this clock. Let's have a look at object detection next. Object detection is different from image classification, in that it also tells us where objects are in the image. We're using TinyYOLO v2 here, which, while it can only detect 20 objects, it quite importantly detects people. We use this in our background replacement algorithm. First, let's take an image of the reference background. Now we'll capture an image with the human subject in the middle. Using TinyYOLO, we'll get a rough bounding box around the person, and we can use this to compare the pixels outside the box with the reference background and use that information to determine which pixels inside the box are in fact the foreground pixels. Let's see how it fares here. So, while it's obviously not perfect, this shows how the library can be used for a real-world application as part of a larger processing pipeline. What do you think of that, Gabby?
That's such a useful library.
Yeah, as you can see, we have really improved user accessibility to deep learning in Haskell. We've built a better interface for users to train networks with. We've built a native app which packages many of the features of Grenade so that a prospective user can trial the potential of the library before installing it. And we've also written a website that serves as an entry point to Grenade with a tutorial on training a network on the MNIST dataset.
Wow, it really sounds like you guys have contributed to the Haskell ecosystem, and you've already implemented a basic proof of concept green screen. Looks like I can take it from here, guys.